This is the third lecture from Chapter 13 about kinetics. And so far we've talked about rate of reaction with respect to reactants and products, their rate of disappearance or appearance. And then the second lecture was differential rate laws, just more commonly called simply rate laws. And that was of the order, the rate equation, rate law equation, was of the order some rate constant K times concentration of reactants raised to some order of reaction. And we learned about the method of initial rates, where you get the table of data and you can determine the rate of reaction and then solve for K. So this lecture is about a second type of rate law, integrated rate laws. You're not going to need to integrate, but that is how they derive the integrated rate laws from the differential rate laws. So the rate law that we talked about in the last lecture, the differential rate law, gives the rate of reaction as a function of concentration, right? But it doesn't say anything about time. So remember how we got these, the values in these rate laws is we had to carry out a number of different separate experiments, all with varying concentrations of the reactants, and then measure the rate immediately, right, before any products built up. But what if, as a chemist, you want to know how the rate changes over time? That's where the integrated rate law comes in. So literally, if you integrate these differential rate laws over time, you are going to get the expressions shown here, integrated rate laws, and you don't need to derive them, but just if you're curious. So let's say that our order of reaction with respect to reactant A is 0. Then according to the regular rate law, the differential rate law, the rate would be equal simply to the rate constant. The rate would be constant, would not be dependent on the concentration at all. And if it was first order, right, so that our exponent is 1, then the rate would be directly proportional to the concentration of that reactant. The integrated rate law for first order looks like this. So just check out the difference in the regular rate law and the integrated rate law. If the differential rate law, it was second order, okay, exponent of 2, then the rate is proportional to A squared, right, concentration squared. And check out the integrated rate law. So at this point, we're going to go into detail a bit about each of them, but at this point, I just want you to notice that each one of them has a factor of time, has the variable time in them, okay? And they all, both of them, all of them, also have the initial concentration of the reactant. That's what this little 0 means, is initial. And then the concentration of the reactant at whatever time you're interested in. So doing a little bit more comparison of the differential versus integrated rate laws. Thinking about the differential rate law, if we were to plot the rate of a reaction versus its concentration using the differential rate law for a 0 order, now remember 0 order doesn't depend on concentration, the rate is simply equal to the rate constant. So you would just get a horizontal line, right? And that line would be equal to whatever K is. For differential rate law, again, for first order, we would have something that looks like this, and the rate would be directly proportional to A. So as you increase the concentration of A, the rate would increase also. So just like any direct proportionality, you would get a linear positive slope relationship. Then for a second order, looking again at the differential rate law, the rate would be dependent on the concentration squared. So that's an exponential relationship, so we have an upward curving, okay, changing faster than the linear. All right, so these are what the graphs would look like if you use the differential rate law to make a graph. The integrated rate law, move that up there. If you, here they are repeated here. That's what it looks like for 0 order, first order, and second order. You can get a line they're all written on purpose in a linear type form. And I'm sure you remember this from earlier days, right? The equation of a line where y-axis, x-axis, m is the slope, right? And b is the intercept. So all of these integrated rate laws are written in that format so that they can be plotted. And so, for example, for a zero order, if you plot the concentration of a reactant on the y-axis and time, okay, that's t, on the x-axis, you will get a straight line. And guess what the slope will be? This, okay? So the slope is minus k. So now you can find the rate constant from a slope. Let's do the same thing for first order. Here was the first order integrated rate law. In this case, if you want to get a line, you have to plot the natural log of concentration versus time. Okay, and again, the slope is going to be minus k. Now, if you had a reaction that was first order and you plotted it, instead of plotting it the natural log of A, if you just plotted concentration of A, you wouldn't get a straight line, okay? You'd get a curved line. So what gives you a straight line with using the integrated rate law is only if you plot the correct variable on the y-axis. Second order, what needs to be on the y-axis in order to get a straight line is 1 over the concentration of A, okay? And again, versus time. And this time, our slope is simply k. It's positive k. It's the only positive slope. All right, so we'll work with those more, but I just wanted you to get a look at them. Now we're going to look in a bit more detail about the 3 common orders you're likely to encounter, and that would be order of 0, 1, and 2. So let's talk about if an order of reaction with respect to a particular reactant is 0. And again, that means the rate is simply equal to the rate constant, does not depend at all on the concentration of the reactant. So just to remind you, the zero order integrated rate law looks like this. So let's say that you did an experiment and you know your initial concentration of reactant and you monitored how the concentration of the reactant changed over time. So you kept track of time and then you kept measuring the concentration. And let's say you weren't quite sure it was zero order. You wanted to figure out what order it was. So what you can do is you can start making graphs. You can make a graph of simply the concentration of the reactant versus time. And then you can make a second graph, which would be log of concentration of A versus time. And a third graph, which would be 1 over the concentration of A versus time. And whichever one of these graphs gives a straight line means that's the order of the reaction. So if it were zero order, you would get a straight line simply by plotting, that's the intercept, simply by plotting the concentration of the reactant versus time. The other ones, if you did plot them, well, no, it'd be curved this way, wouldn't it? If you did plot the others, you'd get curved line, and that would be your red flag. Okay, it's not first order, it's not second order, it is zero order. For a first order reaction, again, here's the differential rate law for first order. Here's the integrated rate law for first order. Again, if you collected data, you would know your initial concentration of the reactant, and then you would monitor as a function of time how the concentration of A changed. And then you would make your 3 graphs to determine the order. So the first graph, right, would be just the concentration of the reactant. The second graph would be natural log, and the third one would be 1 over. And if this were a first order reaction, this is the only one that would give a straight line, the one that was natural log. The other ones would give curved lines. So this is just a more professional looking graph than what I can possibly draw. It's just what I said in the last slide. So if all you did was plot the concentration of reactant versus time, and if it were a first order reaction, you would get a curved slope, period. And if it were first order again, you would get a straight line if you plotted natural log of the concentration. All right, second order reaction. Okay, here's the differential rate law for a second order and the integrated rate law for second order. So again, if you had a second order reaction, you would get a straight line if and only if you plotted 1 over the concentration of A on the y-axis and time on the x-axis. All right, so I know I'm getting redundant here, but again, second order, in order to get a straight line, it is 1 over the concentration versus time. So here's a good summary slide of what you need to know for integrated rate laws. Integrated rate laws are usually used in conjunction with graphs to determine the order of reaction. Whereas the differential rate law, we determine the order of reaction from several different experiments. Integrated rate laws, you just conduct one experiment and just monitor the concentration over time. So it's easier experimentally, but it's heavily reliant on graphs. So here's a nice summary. I will give you the 3 integrated rate laws on your exam. I will not label them. I will not tell you, okay, this is 0 order, this is first order, this is second order. You have to know that. But I will give you the actual integrated rate laws. So again, if when you plot concentration versus time, you get a straight line, that means it's 0 order. If when you plot natural log of A versus time, that is first order. And if you plot 1 over A versus time, that is second order. Keep aware of what the slopes are too, right? That 0 order, the slope is minus K. First order, it's also minus K. And the second order, it's positive K. So that is also how you find the rate constant with an integrated rate law. I love this slide. So if I were a student, I would literally print this slide out. It's very cool. Especially if you're a visual learner, okay? So 0 order, that's the plot that gives the line. First order, second order. It gives you both the differential rate law and the integrated rate law for comparison. We will, a little bit later, it might actually be the next PowerPoint, be talking about half-lives. And that's half-life, as you will learn, is the amount of time it takes for the concentration to deplete by 50%. This is redundant again. However, I like this one especially because not only does it give you each of the 8 rate laws, it gives you the units for the rate constant. So I'd still like you to go through how we get these units, but it's nice to just kind of have them to memorize if you do better that way. So what I want you to notice is the pattern. You may have missed me saying this in lecture, but, oops. All right, 0 order, the units for K are molarity over seconds. First order, it is simply 1 over second. Second order, it is 1 over molarity per second. And to continue the pattern, if I had a third order overall reaction, the units for K would be 1 over molarity squared times second. Do you see a pattern? And that's just going to help you remember. The pattern is with each order of reaction that you add to the previous, you're essentially dividing by molarity each time. So notice that molarity is in the numerator here for 0 order. Then imagine what you're doing each time is you're dividing by molarity for each increased order. So now we got rid of molarity on the top and it's nowhere to be seen. Divide by molarity each time. See, so second order has a molarity in the bottom. Third order has 2 molarities in the bottom. And if we had a fourth overall order of reaction, there would be 3 molarities in the bottom, okay? So like 1 less molarity than the order, I guess. Here's a very simple sample problem that you may be asked, and you would use an integrated rate law for it. So there aren't as many formulas as we had with gas laws, but you still have to know which rate equation to use to solve the problems. So the biggest hint I can give you is if you read the question And anywhere in the question, it mentions time. That means you need an integrated rate law, okay? Remember, integrated rate law is the only one that has time in it. All right, so let's read over the question real carefully. This reaction is first order, all right? They give you that. They give you K. They give you the initial concentration of sucrose. Remember that little subscript 0 means initial. That's what you started with. What is the concentration of this reactant after 2 hours? So that is your clue. You see the time and you're like, okay, I need integrated rate law. They gave you everything you need. So then you would write down the first order integrated rate law, which is natural log concentration at time t equals minus rate constant times time plus natural log concentration of A initial at time 0, okay? And then you plug in all the information they gave you. All right, and this page simply shows the values plugged in. So they told us the initial concentration of sucrose is 0.4. That's this value. They gave us K. And they told us they want to know after 2 hours. So now here's one little thing you got to be careful of. Look carefully at the units for K. Okay, so every first order reaction is the K is going to have units of 1 over time. But the time could be seconds, minutes, hours. But the time has to match whatever units you have for T time, right? Because those units are going to cancel. So you either need to put K into seconds, inverse seconds, or else hours into seconds. So I think it's easier to put hours in, right? So 2 hours is 3,600 seconds, basically. All right, so here's your time in seconds multiplied by K, and you are solving, they want to know the concentration of sucrose at this time that you plugged in. So when you simplify all that, there you get. Now, be careful because what you're going to have is the natural log of the concentration. So you want to get rid of the natural log. So hopefully you remember now, we've done this before, that to get rid of a natural log, and blue on blue doesn't show up, to get rid of natural log, you're going to use E. Okay, so both sides are going to become an exponent for E. Then plug E to the raised to the minus 1.36 into your calculator, and here is the concentration of sucrose after 7,200 seconds. That's plug and chug, really. And that wraps it up. So now you just simply need to practice a lot of integrated rate law problems.